is leaning across there and looking at what you've drawn when you were drawing the atom. So I asked you all to draw a lithium atom. I asked you to draw a sodium atom. And I asked you to draw a potassium atom. And I asked you to tell me what a similarity is between all of these atoms and a difference. And as I'm looking, could you tell me please what the similarity is between these three atoms? Thank you. So you all nicely pointed out that they've all got one electron in their outer shell, and that tells you that they're in group 1 of the periodic table. So they've all got one electron in their outer shell, and that's really important for understanding and explaining why the alkali metals, lithium, sodium, potassium, and the others in that group, why they behave in the way that they do. Now in this topic, we have to know all of the properties of those alkali metals, these three alkali metals, from memory. So we're going to look at them today, going to write them down and try and memorize them and learn them. We also got to be able to explain some of those properties as well. So we're going to go through all of that bit by bit. I asked you for one difference between the alkali metals as well. So tell me what that is, please. So the key thing, as you pointed out, is they've got a different number of shells. Lithium's got 2 shells, sodium 3, and potassium 4 shells. And that tells you which row or period of the periodic table they're in. So second period, third period, fourth period. Because it's got 2 shells, 3 shells, 4 shells. So what we're going to do, we're going to move straight to a demo, and I'm not going to record this, of looking at these elements and thinking about how they behave and react. Let's do that now. So we just went through looking at all of the demonstrations of lithium, sodium, potassium reacting with initially air, but also water, and we looked at their physical properties too. So let's just go through what we found out there. So lithium and sodium and potassium, one thing that's in common with them is they're all solids at room temperature. Of course, they're metals. The only metal that's not a solid at room temperature is mercury. And we talked about metallic bonding in the previous lesson, so I'm not going to do that now. We just tested on that last lesson. What you need to know is that all of them are soft, but as you go down the periodic table, they become increasingly soft, and we can see that they're soft because we can cut them. So they're soft and they get increasingly softer as you go down, and we know that because they can be cut with a knife easily. And when I cut them, you can see that they tarnished easily. So as you go down from lithium to sodium, potassium, when I cut them, I showed you how shiny the surface was. So they were shiny when I cut them, but they tarnished very quickly. That tarnished more quickly as you went down the group. And we'll talk about the explanation for that in due course. And what they mean by tarnishing, as we said, was they can react with water in the air, so moisture in the air, moisture, or oxygen in the air. And that forms oxidation products, we'll say, on the surface. We'll leave it like that rather than get into the detail of it. You don't need to know what's going on there exactly. Okay, so we know that they're soft. We also noticed all of them have low density for metals, which is really surprising, because we know this because they float. I'll try that again. Float on water. So that's linking the property, they float on water, with the explanation, their low density. So we don't just say anything in isolation. So these are soft, and we can show that because they can be cut with a knife. We're not going to try and explain that, but they're soft. And we're going to explain the reactivity in a bit. The low density, we know that because they can float on water. Now, I wanted to talk about the reactivity, but I'm going to start with about the things that were in common about the reactivity. Sorry about that. So we're going to concentrate on the now the things that they have in common. So in terms of the reactivity. So when they reacted, little heading of reactivity. When they reacted, the thing we're going to concentrate to start with on the things that are in common. So they all fizzed, and we learnt that that's because they produce hydrogen. This is a chance to remind you that hydrogen is diatomic. It's H2. There's two of them in the molecule. It produces hydrogen. Right? So they all fizzed. They all moved around on the surface. And you've got to be able to say all of this in an exam, right? All moved around on the surface. And that's because they're fizzing and low density. They all eventually disappeared. Dissolved. But I prefer to say really that they disappeared because they fully reacted. But be clear that eventually all of the metal has disappeared in the end. So that's something that's in common with all of them. And I showed you also at the end that they produced an alkali. That's why they're called the alkali metals, not because they themselves are alkaline, but because they make an alkali when they react with water. So the pH of that water was about pH 14 once I finished messing around with it until we got indicator paper or indicator, universal indicator would have turned blue, purple, right? And the thing that's produced in each case with the metal hydroxide, I'm going to remind you that the hydroxide is OH minus, and so in each case it was lithium hydroxide or sodium hydroxide or potassium hydroxide. These were aqueous, in other words dissolved in water. So we couldn't see those things, but we had evidence of them because the indicator turned purple. Right? So that's the thing that's in common with all of those three metals. I'll pause for a sec. They're the similarities between all of them. They all did essentially the same thing, but there's some differences that I want to highlight too. So this is the similarities. The differences first of all, we saw the sodium melted into a ball, or became a molten ball if you like. And that's because its melting point's lower. It's also a more exothermic reaction. So we saw the sodium melt into a ball. And as you go down the group from lithium to sodium to potassium, the reaction became more vigorous. The effervescence was greater, so more fizzing, more vigorous, faster fizzing, and faster movement on the surface. And they disappeared faster as well because they reacted faster essentially. So they reacted faster. And we're heading towards an explanation for that. To think about what happens when they react in a moment. They become more vigorous, faster fizzing, faster movement, reacted faster. Okay. This next bit is crucial. This is where the big marks are. This is this explanation for why the order of reactivity down the alkali metals is what it is. They increase in reactivity you've got to know and be able to recite and recount in any exam. It's a very, very common question. So I'll walk you through it, pause the video, and you can catch up with just writing it up. So let me just once again, I'm just going to compare lithium and sodium. I could make the same argument for potassium, but it's exactly the same thing. So I'm only going to make it for lithium and sodium. So you pointed out earlier on, they've got one in their outer shell. And what you might remember from the whole ionic bonding topic, or what you might not remember from the ionic bonding topic, is that when metals react, they react by losing the outer electron or electrons. All right? So lithium, when it reacts, turns into a lithium ion. We end up with a full outer shell and a 1+ charge, right? Sodium, when it reacts, it loses an electron to end up with a full outer shell. You end up with a 1+ charge. So they both form 1+ charges, both end up with full outer shells like that. And that electron goes off and does some reactions. I'm not going to explain that bit of it right now. And we've got to decide though which of these two processes is fastest: lithium losing an electron or sodium losing an electron. Ice front, please. Lithium loses an electron, sodium loses an electron. Which one does it faster? Sodium or lithium? 3, 2, 1. Sodium, of course, right. So it reacts faster. That's why it does all it is. So this one's faster. So it loses its electron more easily or more quickly. More easily. And why would it do that? Now what we've got to think about is what's holding the electron to this atom. So sodium sitting in that oil over there would happily sit as sodium, the metal, the atom, for a very, very, very long time. But as soon as we give it a chance to lose that electron, we let it react with oxygen in the air or water or some other stuff that we'll talk about in a bit, it'll lose that electron. So what's holding that electron to that nucleus? Well, we're going to think about what's in a nucleus. We're going to think about what chemistry is all about. And we know that nuclei have got protons and neutrons. We know from the topic that we've just finished that protons, the nuclei, are positive. And so there's an electrostatic attraction, folks, isn't there, between the electron and the nucleus. Between that electron and that nucleus, and between that electron and that nucleus. Right? So, the reason that sodium loses its electron more easily than lithium is because it's a weaker electrostatic attraction. Between nucleus and the outer shell, or the outer electron. And why would that be? It's simply because it's further away, right? But we're going to really think about this and how to answer it properly. So the force of electrostatic attraction, bit of physics for you, is proportional to 1 over the distance squared. In other words, if you're twice as far away, eyes front please, the attraction is 4 times weaker. So twice as far away, 4 times weaker. This electron is further from the nucleus of sodium than this electron is from lithium. So this force of attraction is weaker, and so it's overcome more easily. So it loses its electron more easily. So weaker electrostatic attraction between nucleus and outer electron. And we first of all say that's because there's greater distance, and that's because there's more shells. So more shells, or another shell, and greater distance. Between E and nucleus. But there's another reason we need to really add in here if we want to do a really good job of this, which will hold firm even when we go do Key Stage 5 chemistry, which we've got to think about the number of shells in between the nucleus and the outer shell. Now, inner shells do a process called, cause a process called shielding. They shield the electrostatic attraction between the outer electron and the nucleus. And so the more shells you have, the more shielding there is, and the weaker the attraction as well. So that's another thing we can add. All that shielding is, for those of you who want to know a little bit more than you need to, is electrostatic repulsion between that electron and the inner electron. So they're actually just pushing each other away. You don't really need to know that, but I quite like to include it in my discussion. So we can also say that the electrostatic attraction is weaker because there is greater shielding due to the extra shell as well. Now, I'm not going to add any more to your notes here. I just want to say to you that you might spot that that's slightly surprising. The nucleus of sodium does have more protons, and that is important. But even though sodium's got more protons and that therefore would have a greater pull, you might say, the extra distance and the extra shielding is a much bigger factor, so sodium loses electron more easily. And you can make the same argument for potassium, you can make the same argument for rubidium, make the same argument for cesium, and we'll have a look shortly at some videos of rubidium and cesium reacting with water. So notice that I've also added underneath balanced equations for the reaction between the alkali metals and water. It's the same for all alkali metals. You will need to practice this, we'll practice it in class and we'll learn it. You need to know that you get 2 of the alkali metal, 2 of the water, to make 2 of the metal hydroxide, like lithium or sodium hydroxide, which is the source of the alkali, the OH minus, the hydroxide. You also generate 1 molecule of hydrogen, which is why we get the fizzing. And it's that gas, the hydrogen, which catches fire in the case of potassium, giving you that lilac flame. You get a lilac flame for potassium. We'll come back to the lilac flame thing in a future lesson. But these are the other reactions you need to know. I've added one more at the bottom, which is this one here, which is just to show you that alkali metals can react with halogens as well. So this is the reaction with halogens. And they all work in exactly the same way. Doesn't matter which alkali metal, which halogen, you get the same reaction going on. Metal plus halogen, so Cl2 or Br2 or F2 or I2, gives you the metal halide. And we'll talk about that more as well when we get to the halogens topic in a future lesson. Okay. So just for the last few moments of the lesson, just practicing a few of these bits and pieces, and trying to get our heads around it. So that's it. That's it for the alkali metals. That's what we need to know essentially.